All right, hello calculus students. Today we're going to look at a new kind of solid volume problem called solids of known cross-section. So for the first example, I wanted us to consider the sine function and the area trapped between it and the x-axis, just between 0 and pi. So basically the area under the sine function between its first two x-intercepts, and instead of revolving that around various axes like we've been doing in 7.2 with solids of revolution, and the washer method and disk method and all that, I want to this time find a solid of known cross-section where we look at semicircles as the cross-section. So this is the kind of problem that you're going to probably be using mostly for your project this semester, because you're going to have a blank space, a blank page, a poster board, a wooden board, a metal board, whatever you decide to make your project out of, and you're going to want whatever your design is to rise off that page. And that's basically what a solid of known cross-section does. You can definitely use solids of revolution in your project as well, but I think you'll be using these most often. So basically any shape that you know from basic geometry where you know its area formula can be turned into one of these. So semicircles, quarter circles, rectangles, squares, different kinds of triangles. We'll see a variety as we look at this lesson. So let's start out with this simple one. So first, of course, you need to make sure that you draw what you're trying to do and try to visualize it before you do anything else. That's absolutely key. So the sine function is going to look something like this. That's 2 pi. Remember, they just wanted us to go from 0 to pi in this particular problem. So I'm just looking at these two x-intercepts and the area between them. So we're going to use semicircular cross-section. So I'm going to draw one of those. And you should imagine this cross-section coming out of the board at you. So semicircles coming out at us like this, if you will. So the tallest part that's going to come out at the board is going to be like right here at the peak. That's going to be like this far out, like that far out off the board. As you get down in here, the semicircle is only going to be shorter, and it's going to get very short. So you can see it's going to peak off and then go back towards 0 height as you go into the board. So notice we're not doing any revolution. So we might use pi on some of these, but not as often. The area of a circle has a pi in it, so this problem will have a pi. But don't count on a pi being in every problem. All right, so we're doing a volume again, imagining this is one green cross-sectional slice. We're going to have a whole bunch of them. The way we get volumes is just like the way we did it in the last section, where you integrate from where you start to where you end. So we're integrating from here to here on this problem, 0 to pi. And what you want to do is integrate the area formula for the cross-section that you're using. So we're going to integrate area of a semicircle. So in fact, you know what, I'm just going to put a of x. And it's green there. Let's be color consistent. We'll make it green here. So a of x dx, and dx is going to be, again, just like we've been working with our infinitesimal rectangles. It's the width. When we integrate or add up all those dx's infinitely between 0 and pi, where their lengths go to 0 with the integral, we're going to get the volume, and the precise volume, not just an estimate. Okay, so for this one, what is our area formula? Our area formula is a semicircle, so we're going to have pi r squared dx, and it's a semicircle, so it's going to be over 2. So let's simplify. We've got 0 to pi. Pi over 2, I think, can come out on this one, so let's take that, factor that out of our integral. And now we've got to think about the radius. So this is the part on this problem, and many like it, that you'll be working on where people make mistakes. A lot of people are going to say, okay, I've been working with the function, the height of the function on a lot of problems, so I just put sine of x in there, right? This function right here is f of x equals sine of x. That's true. But if you look at the height, that's this whole distance. Is that the radius of this semicircular cross-section? Or is it the diameter? It's clearly the diameter. The radius is just going to run, let me grab a red, from here to here. So that's what we need to be plugging into our area formula for the integral. There to there is the radius. So how high is that? Whether it's there or over here, it's going to be half of the function's height. So r is going to be the function height, which is sine of x, cut in half and squared. So there's our integral that we need to do. So let's do it. We've got pi over 2. I'm going to square this stuff. So that is, I'm going to square the top and the bottom. So that's sine squared x over 4. I'm going to bring my 4 out in front. So you can see there were a lot of 2's here. There was the 2 from half the area of a circle, and there was the 2 that's inside the squared from thinking about the radius and not the diameter appropriately. So we're going to take that and we get pi over 8 times the integral from 0 to pi of the sine squared of x. So at this point, if we're in chapter 7, as we should be in our class, you're going to have to know a more advanced integral technique. And it's really not a very more advanced one. We could have done it last year. It's just using an identity. So I'd actually challenge you to try to do this problem on your own using the identity. There's an identity in your book which will change this from a problem we can't do to one we can. I'm just going to go ahead, and you can if you run into an integral with sine squared or cosine squared for this chapter until we get to chapter 8 where we learn how to do them. You can use Math 9 on your calculator. So I'm going to go ahead and get this guy from Math 9. So I'm going to go pi divided by 8 and multiply that by the integral from 0 to pi the sine of x all squared dx, making sure I am in radian mode. I am. And I got that my volume was going to be 0.617 units cubed. Just for anyone who's curious, I'm now going to show how to do this integral the correct way from chapter 8, even though we haven't gotten there yet. So let me erase this guy. Let's look at how to do this integral correctly from chapter 8. So you just use an identity. You say, okay, we've got pi over 8, integral from 0 to pi. So let's see, I think we go and use a half angle identity. So the sine squared of x is actually also equal to something over 2. I believe it's 1 minus the cosine of double x over 2. I'm going to check that real quick because I haven't used it for a year or so. And I was correct. It's actually in the front of your book, one of the identities there. So this is an identity we'll be using a lot in chapter 8 to do trigonometric squared problems that we couldn't do otherwise from Calc 1. So let's see if we get the same answer. So we've got pi over 8, and we need to integrate this. So I'm going to break this apart like this. That's 1/2 minus the cosine of double x over 2 dx. So that's going to be pi over 8. Integral of a half is 1/2 x, evaluated between 0 and pi. And then we've got minus pi over, if I put this and this together, that's pi over 16, pulling that half outside of the integral. And here we've got the cosine of double x, which I think is something we can do. That's a 2x there, sorry. Unlike cosine squared or sine squared, which we couldn't do. So this one's going to be pi over 16 times pi minus 0. That's nice and easy. Pi over 16. You got to do a u sub here, or think Zen method in your head. So you got to compensate for that chain rule by taking a half. And the integral of cosine is positive sine of 2x from 0 to pi. Let's see what we get. So that's going to be pi squared over 16 right here, minus pi over 32. I can pull that out too. Pi over 32 times the sine of 2 pi. Sine of 2 pi, y-coordinate, as we go around right here, the y-coordinate should be 0 or 1. It's up and down, that's 0. When we put 0 in, we also get 0. So I think that's really just going to be pi squared over 16. I'm going to check that in my calculator, see what I get. pi squared over 16, and it's 0.617. We're good to go. So there's how to do that integral from chapter 8. Something that's good to know. You'll actually be ahead if you try to do whatever sine squared or cosine squared problems like that. Not very hard. Let's look at one more solid of known cross-section in this video. So let's consider the region bounded by a different function with a different cross-section. So let's consider the region bounded by, let's say, h of x. You know, I'm not going to give it a function notation. Let's use an ellipse. So let's say x squared over 4 plus y squared over 25 equals 1. There's an elliptical base region centered at the origin, so nothing too complex yet. We'll do more complex problems soon. But we're going to consider that region, and let's form cross sections using squares perpendicular to the x-axis. And let's just do the entire base region, okay? So first we want to draw. So I'm going to draw my base region. That ellipse goes out 4 or 2 in the x direction. You should be telling me 2 in the x direction. So we're going to go out 2 in the x direction. And we should be going out 5 in the y direction. There's no transformations in here, so we're sticking right with our ellipse centered at the origin. There's nothing that says a problem has to maintain that simplicity. On your project, you're going to probably be wanting to make ellipses go other places. Okay, so this is a crazy looking ellipse. Sorry if my ellipse doesn't look perfect, but I think it gets the job done here. So our square cross sections, we want to be perpendicular to the x-axis. Let's just write x perpendiculars like this. So let's imagine one of them. So one of them would be like from here to here, wherever that x value hit. It's like that's like an x of like 1.6. I'm just drawing an arbitrary cross-section spot. So that is going to be a square. So let's see if I can eyeball a square. Something like this. Okay, so you could shade all that guy in. I'm not going to shade it in this time. It's going to be too much red. So you can see that, again, we're going to have the highest part of our volume right in the middle because it's going to be a square that goes like this, out, and over here it's going to be going farther down, farther down, farther down, all the way down to nothing. So it's going to be falling off both ways. And that's the kind of cross-section, strange shape you're going to get for this. Kind of neat, I think. So let's find its volume. So the volume this time is going to be the integral from, I think we're again doing vertical infinitesimal cross sections. You can do horizontal ones. We'll be working on those in another lesson. Let's stick with vertical today. So we're going to go from -2 to 2. Gotta get rid of this fly, holy moly. So -2 to 2, just like last time, we want to think of the area as a function of x and dx. So what's that going to be? You're used to, on these problems, probably a lot of pi's. There's no pi in the area of a square. So this is really just going to be side squared dx, which is going to be what? So we just got to figure out how long this side is, and then we got to square it right there. So I'll write that in red. So this is the side length, which goes from the top to the bottom there. So how do you figure out how long that is? Well, the only thing you really have the ability to measure or think about here is how high the function is. So from here to here is the height of the function, in other words, y. So if we get that y out of our ellipse equation and double it, we'll have the side. So my side, let's write that down right here, my side is going to be whatever y comes out of there. So let's do some scratch work up here. So I'm going to solve for y, subtract this to the other side, of course, multiply by 25, and square root. Oh, that got messy. 25 minus 25 fourths x squared. There we we go. Let's see what happens. So that's the side. The side is going to be double what I call y here in blue. So I had it in red. I guess I'll stick it in red over here. So we're going to go 2 times the square root of 25 minus 25/4 x squared, and that all gets squared. There we go. So going through it one more time, because the setup is by far the most important here. This is y. If you double y, you get the side length of our cross section. If you square our cross section, you get the area of the cross section, which is here is in red. If you integrate that cross section from -2 to 2, you get to add up all those squares this way and this way, and you get your volume. So there you go. So now we just got to do the integral. Let's see if this one turns out simple or not. So 2 squared is 4. I'm going to take that out of my integral. Square root and squared cancel, thank goodness. So we just have this guy left. From -2 to 2. Ah, that's a pretty easy integral dx. So that's going to be 4 times the 25x minus 25/12 x cubed, because I go up 3, divide by 3. I just need to work that down. So let's see, I've got 4. Let's give ourselves some more space. 4 times the integral of 25 times 2 is 50. I'm just going to do that. So dropping 2 in with the fundamental theorem, dropping 2 in the fundamental theorem, and dropping the -2 in. Negative cubed is going to be positive and make this 25/12 times 8. See what we've got here. We've got 50 plus 50. That's 4 times 100. And then we've got minus this thing, minus that thing. So that's going to be -2 of those things. So let's just say -2 times 8 times 25/12. We've just got to simplify that over here, and we'll be done. So we've got 400. I'm just going to distribute that 4 minus 16, distributing the 4. I have a 25 there, and I have a 12 on the bottom, so that's 400 minus, let's see, 4/12 is 1/3, so it's going to be 400 minus, let's see, 16 times 25. That's like 4 times 25 is $1, so that's going to be 400/3. So let's see, 400 minus 400/3. You can make a common denominator by going 3 3s, so that's 1200/3 minus 400/3. So that's 800/3, or about, what is that? Ah, I'm getting tired today. I'm going to go to my calculator. 800/3. It's about 266.667 cubic units of whatever kind of measurement you have. Remember, a calculus test, you want to make sure you get to the 3rd decimal place. It's really just safer to leave it at 800/3. All right, so in the next video, we'll look at a different cross-section again. We'll look at an equilateral triangle that has a sneaky, like, 1 number thing for the height of the triangle in it. And that'll be it. So I'll see you next time.